So we've got another Candida presentation. This one is not the same one that was just done across the hall. So if you're coming over following these fine gentlemen, you're in store for different material. So first off, we've got Shan Arora. So Shan is the director of the Candida Building for Innovative Sustainable Design, a multidisciplinary, non-departmental education building on the Georgia Institute of Technology Atlanta campus. It is the first building in Georgia to earn Living Building Challenge certification, the world's most ambitious and holistic green building achievement. The mission of the building is to be a catalyst for change in the region and beyond. Being a regenerative building, the Candida Building proved over 12 months it gives back more energy and water than it consumes. Shan's role is to promote the building and the regenerative building ethos in a way that create a better built environment. Before this role, he was at South Face Institute for 8 years, and before that, Deloitte Tax. Shan obtained BA and JD degrees from Emory, has received Living Future accreditation, and this is random, is a licensed U.S. Customs broker. Shan also serves as on the board of directors of Georgia Interfaith Power and Light, and
he played linebacker for Emory's football team.
Oh, there we go. Yeah. All right. Next up, we've got Joshua Gassman. So Joshua is a principal and sustainable design director at Lord X Sargent Planning and Design, located in Atlanta, Georgia. His practice is dedicated to the holistic execution of complex, sustainably focused projects. With a broad portfolio of diverse clients, his career centers on technically challenging projects with large, multifaceted consultant teams. And an avid environmentalist, Joshua has extensive knowledge of USGBC's LEED system and other sustainability verification systems, such as Living Building Challenge. His experience has resulted in exceptionally high-performing buildings, including net positive water, net positive energy, net positive waste buildings, including the Candida Building. Let's see, he's a LEED accredited professional, NCARB holder, and member of many professional organizations. I'm not going to read them all out. All right, I know.
Enough.
You want me to? I'm going. All right, Jimmy Mitchell. Jimmy started with Skanska in 2005 with a bachelor's degree in civil engineering at Georgia Tech. Sustainability is a career position, one of Georgia's first LEED managers, created the Atlanta Mission Urban Garden, and was a founding member of the construction material reuse nonprofit based in Atlanta, the Life Cycle Building Center. His current role with Skanska is the Senior Director of Business Development. His project experience includes the Candida Building, this. All right, I'm going to hand it off. Thank you, gentlemen.
Thanks, Michael.
All right. Wait, you let Shan touch the technology? Okay, there you go. Okay, so thank you everybody who followed us across the hall. It looks like a lot of people did that. I'm flattered. For those of you who were not at it at the previous session, doesn't look like there are too many folks, but for those of you that weren't, we are representing the contractor, the owner, and the design team for the Candida Building at Georgia Tech. And this session, we're going to try to keep super fast and loose, if that's a thing. I think we're actually very interested. We have some graphics that go with different lessons learned and different stories that we can tell, but we're actually really interested what lessons learned people are interested in. And so we kind of, I don't know the best organized way to do this, something like shout them out to us. Maybe we start with that side of the room and kind of move across this way so it's not total chaos. Yeah, so, all right, so the options from which to choose include energy and performance, water, materials, programming. What else was in there?
Hot off the presses, not yet released. Return on investment.
Yes, return on investment, if you want to hear about that. Yeah, that has no graphics, that's just talking. And we can talk about structure? Sure, absolutely. We can talk about, we can talk about, and actually, I think between the three of us, we know more than any other 3 people put together on the planet about the building, so we can probably speak modestly intelligently about just about anything anyone's interested in. So let's kind of leave it at that.
What were some of the difficulties in designing around attaining that more energy generated than used?
Okay. All right, that's good. Do you want to just go across the room and get a bunch of topics, and then we can bounce between them?
That was how do you design for net positive energy, and what was the challenge in our particular region?
The structural guys in my firm would look at that and shudder, just with the solar panels being a sail in the wind. And my other question would be, what do you do with all the water that shows up in the cistern?
Okay, those are good. Good.
Structure, a sail in the wind, which it's kind of designed to look like. And what do we do with the extra water in the cistern? One more.
Other thoughts?
Got it. Okay.
ROI, all right.
When you talk about the energy systems, talk about M&V and how you plan to continue M&V over the building.
All right. M&V, ROI.
Recycling, using recycled materials, and also you had a whole institution helping you define those kinds of things.
Yes. The circular economy, circular systems. Okay. So let's one more. Okay.
Couple more.
Okay. Yeah.
So, does Georgia Tech operate the building?
Yes.
Yeah, Georgia Tech is the owner.
Did you have to convince maintenance staff about exotic systems like gradient slabs and whatnot?
That's
How did that go?
that's a good topic.
And
too.
that actually goes into. So why don't you start with energy broadly, and that includes this funky design right here that's giving
So-
heart palpitations to our
so
friends.
let's start just because it's on the screen. We can start with this. So one of the goals. So when we think about energy, I want to think about energy in it's the same umbrella, but it's 2 different things, right? So it's operational and it's embodied. And so a lot of time has been focused in the design industry on operational energy in the last, say 20 years or so. But in the last 5 years, everyone has kind of figured out, wait a minute, embodied energy really, really matters as well, okay? And so Sean's going ahead with this joke that he's like...
It's your joke. I love it.
Yeah, no. So, but at the end of the day, when we start to think about both of these things, we want to understand that technology and efficiency are not the same thing, right? And so here, 100 years apart, Ford Model T, Ford Explorer, where did the energy for the technology go? Where did the brain power go in these two vehicles, right? Look at the horsepower, 13 horsepower versus 283 horsepower. We put all of our brain power into making it stronger and faster, and none of it into making it more efficient. It's a much more technological thing, but it is not an efficient thing, right? And so there's a lot of lessons we can learn from that and extrapolate. So. Last longer, I would beg to differ, but that's a different. That's a subject to interpretation. But anyway, so where I was going with the structural thing, though. So in an effort to reduce embodied carbon, one of the things we looked at in all of the structure of the building was to optimize structural materials. Right? It's predominantly a wood building, but it has steel where it wants steel. Wood is a really good material in compression, but it's terrible in tension. So we want to supplement that with steel where it's in tension. That's why you have the trusses on the inside with the steel bottom cords. Well, on the outside, wood is also susceptible to things like decay and insects, and so it's not a good exterior material in the southeast. And so most of our most of our structural elements outside then are steel. Well, if you designed these columns, which are at the height when the building steps down about 40 feet tall, if you design that column out of a conventional steel tube, it would be about 18 or 20 inches in diameter, right? And it becomes kind of clunky. It's not really a beautiful thing anymore. And it uses much more steel, right? More weight per linear foot than the system we've designed. And the way we did this is the very slender column in the middle, the tube, takes the gravity load. And then if you look at the moment diagram on a column, right? Its loading diagram, where it wants to fail is in buckling. And so that's exactly what we've done, is we've braced it against buckling with the minimum amount of steel possible by splaying it out, and then that's where our strength comes from.
And everyone says it looks like a sail, and they think it's beautiful.
Right.
Yes.
It's also, don't forget, this is an engineering school, so putting those types of concepts on display, and you can look at the building and literally see the moment diagram in the building, is important in terms of didactic and reach out to the community, and maybe especially even to younger children that may visit the building and say, oh, why is this way? It's a great explanation. So. Okay.
So I want to add to it, because did a great job doing that both externally and internally. But from how the liability of the structure in terms of the sail is that you end up having some interesting delineation to where it stops and ends, right? Because there's going to be like a 135 mile per hour wind that is going to be your engineering threshold, and then you've got to be smart about who owns the bolt that connects the steel structure to the the PV system, and that takes some time to work through actually, and to get it right. So and you might find yourself in a situation where one group is saying, yeah, I'm good with the panels and the aluminum framing under the panels, and the other group saying, I'm good with the steel structure, but nobody's good with the bolt, right? And so now you got a bolt problem or whatever. So you just got to be smart about that. The PV folks owned the bolt in this case. The Usen and Case didn't want to own the bolt, who is our steel structural engineer.
This slide right here helps continue the answer to the question about energy.
Right. So, all right. So focusing on operational energy now. What you see, 108 EUI, that is the average similar building in a similar climate across the country. It's a CBEX number for those of you familiar with the CBEX database. So we knew we needed to do way better than an EUI of 108. Let me stop myself. Does everybody understand, or is everybody familiar with the term EUI before I go diving down this rabbit hole? Okay. So EUI stands for energy use intensity. It's measured in kilowatt hours per square foot per year. You can think of it as a miles per gallon rating for a building in terms of how much energy it uses. If you're KBTU, thank you. Yes. So it's always good to make sure that I don't misspeak. I am an architect, not an engineer, after all. So through the design, we worked with a lot of different components to try to get to the net positive goal. And if you go back one slide, Sean. So one of the big things we did was we wanted to make sure we understood what made people comfortable, right? Why do you condition a building? Well, a building like this gets conditioned because you want people to be comfortable in it. Most buildings only think about temperature and maybe humidity in terms of keeping people comfortable. And they omit things like air movement at their own peril, because I bet the folks at the table in the back there are kind of cold, because I sat there this morning and it was freezing cold, because you have air movement from 55-degree air coming out of the system blowing on you, and it sucks. You can always pan hotel HVAC systems. They're never good. And so we wanted to make sure we paid attention to all 6 of these in some way, right? Now, we can't tell what clothing level to wear. That's kind of hard. But we can make assumptions that students coming in the summer will be wearing shorts and T-shirts, and that the administrator that's wearing a suit and a tie, well, they're just going to be warm, and that's their problem. Yeah, learn how to dress down, it's okay. And so making sure that we understood this comprehensively, and then thinking about how we zone the building. So not every room in the building has the same set points, for example, right? The lobby, which is more open, is actually allowed to drift higher in the temperature-wise in the summer and cooler in the winter, because people are coming directly into that space from the outside, where they should be, fingers crossed, dressed appropriately for the weather outside. So that was a big deal. If you go to the next slide, back to the performance. So we modeled that, but our performance modeling went down into the nitty-gritty details, including things like there's a coffee stand in the building that currently doesn't have a user, but we talked a lot, maybe too much, about whether espresso versus drip coffee versus cold brew was the right answer because of the amount of energy each of those systems used in the building when we were modeling it. So put all of that together and the safety factor.
Cold coffee.
From an energy standpoint, cold brew.
Yeah.
Espresso is like a lot of
Water's best.
Yeah.
Just
So-
kidding.
So where all this takes us is we also, the mechanical systems and the envelope are really important in this. And so mechanical systems, I think we've touched on already, right? Radiant heating and cooling with dedicated outdoor air system for ventilation. The envelope is very robust. We're insulating well beyond code. We actually went to the point that we have triple pane glass in the building to make sure that the radiant system capacity wasn't exceeded because it's only a couple of BTUs per square foot, and we wanted to make sure we didn't require another system be added at the perimeter, for example. And so all that gets kind of put into our model, and we showed a performance of about 30 EUI. That's where we then say, all right, with an EUI of 30, we now know we need X square feet of PV. That translated to about 330 kilowatt system. And what happens then is we say, okay, this is all good. We're going to go build it. And we should make our target. And we build it. And the first year the building was open, which admittedly COVID overlapped it, but we actually did some simulations to show as if the building had been occupied. And we ended up with an EUI of about 17. And that's the 250% or 240% that we referenced in the last session from the first year it was open. So.
And so, I would say a lesson learned from here, which I will dive in more detail when we talk about ROI, is we definitely over-engineered the building. And to answer your question, sir, for the last, we know that the next projects are going to take less time because we did overthink it, we did over-engineer it, and that was part of the reason it was 100% donor funded. It gave us the freedom to do that.
Just imagine in terms of the overthinking, you finally are in a room of these amazing folks who are consultants. They finally get this project that's actually going to do something like this, right? So, we would consider 2, 3, 4 options and kind of have this great study to then say, you know what, we really, we don't want to do geothermal. We're going to tie into the campus chill water loop. And, and so the design effort was extremely thorough. And then when you go to the submittal stage with the subcontractors and the general contractor and everybody, everybody's a little terrified they're going to make a mistake, right? And so then a lot of extra care was taken to make sure nobody made any mistakes. So I think, the next time, like I said, if the building had burned down and then we built it again the next day, I'm sorry for saying that again. It would be much quicker because we would know exactly what was the right decision at that point.
So I would say one of the big lesson learned to me about this as an architect is that invest in your envelope. I mean, if you look at the performance of this building, what we see when you look at the data, this building is the most carefully monitored building on Tech's campus, probably by far. And when you look at all the data for the first year and after that, what you see is that we really, the radiant cooling system comes on relatively little. In fact, to the point that we may not have needed the system at all. I wouldn't want to say we don't or won't need it with global warming and climate, all these other things that could be coming at the building. But right now, invest in the envelope and then lower your system loads as much as possible and then go for the most efficient system there. It doesn't necessarily have to be radiant. So, yeah.
Clarify on the envelope, it was not in the other session, whether you are implying investing in insulating in the envelope or are you air sealing the heck out of the building?
Yes. Yes.
Yeah.
So for the folks that couldn't hear or for the recording benefit, the question was about air sealing or insulation or both, and the answer is both. Now, I do think return on or the optimization curve of insulation is really important. And I mean, I said before that there was a lesson learned associated with that I'll talk about for a quick second. I think we didn't pay enough attention to the type of insulation that we were using with respect very specifically to embodied carbon, right? This building has, in my opinion, in hindsight, too much blue board in it, right? But this is also before the green board with the lower emission impact was available on the market, right? It didn't exist at the time, but there are things that we, if I had to do it again, we'd pay more attention to. And optimizing
Yeah.
insulation as well. Air sealing, though, I would never back off of air sealing, especially not in a humid climate.
So that's another lesson learned, but I want to make sure the MV question gets.
You just kind of touched
Yeah.
on it about it being well instrumented. So
Right.
can you talk a little bit more about that?
Yeah, so if you can think about, for those of you familiar with laboratory design, right? Think about how the level of controlled systems that are in a typical like chemistry lab, and then apply that to a building that has classrooms and no single pass air in it. And that's what our control systems are like, right? So all of our controls cost is comparable to a wet chemistry lab in terms of cost per square foot. So we have water is metered, sub-metered, and then sub-metered again. Power is the same thing. All the panels are separated. So we understand plug loads, we understand HVAC loads, et cetera.
I want to make a
separate.
point. This was not
Yeah.
necessarily a living building challenge requirement. This
Yeah.
is like a Georgia Tech. The mechanical engineer of campus really wanted to toy with it. So it is a control system and an integrated automation system, so you can remotely access the building and see how it's performing. A ton of, especially for that first year of measurement period, a ton of eyes are on it, and they still are. So we really, when Sean, we'll talk about the ROI study. We've been in the building for almost 3 years. The data we have on it is true data. I mean, we really know. I think we have something like 6,000 data points that are live and active all the time on the building.
But that does bring up a lesson learned. And as one of the operators of the building, I sometimes say a building can be too smart. A little bit of dumbness in a building is not a bad thing, and that's that the building is designed to go to sleep, especially on the weekends. Problem is that sometimes we got events on the weekends. It's rare. And unless I let somebody who has control of the building automated system know, then the building's asleep. And there's no manual override. And that has caused trouble. Sometimes a building decides to go to sleep at 6 p.m. on a weekday. I'm like, why is this happening? And there's no manual override. So and then this, I want y'all to just take a look at this image right here because I'm going to be referencing it in it's a automated exterior blinds, and we'll be talking about that in lessons learned. Ma'am, can you remind me, what was the topic that you wanted to talk about? Yeah, didn't you have something?
Yeah, I want, like, monetizing the health benefits.
Right, okay, we'll talk about that in the ROI section as well.
Why don't you want to just go talk about
so
ROI?
let's
Yeah,
go
just do
with
that.
ROI. First thing I'd like to say is that the building is an R&D project. If you look at the price of the first commercially available cell phone in 1983, it would be $12,000 in today's cost. This smartphone, which is very different than that phone in terms of functionality, the average cost of a smartphone in the United States of America is $530. The point I'm trying to make there is technology has a curve, and that's because of reduction in soft costs, a reduction in hard costs, improvement in supply chain, et cetera, et cetera. It would be unfair to judge the return on investment, the monetary return on investment of a future regenerative building in our area based on the monetary return on investment of this building. Second thing is Georgia Tech is a nonprofit, therefore is not able to avail itself of the federal investment tax credit for solar. It also is not subject to all of the fees by the city of Atlanta or the requirements of the city limits. So there's benefits, cost benefits there, and cost, let's say, a strike against you. So we also pay a ridiculously low per kilowatt hour blended electricity rate of about 6-ish cents. The average commercial customer in Atlanta is going to be paying 11.3 cents. All right, so there are differences. What we did is we said, all right, what is our Georgia Tech's cost premium? About 16%. Compared to our baseline building, which is the same exact building built on Georgia Tech's campus to our 2015 design guidelines. It's a 16% premium.
I just want to add to that the market conditions since we have built the building is much worse than 16%. So the premium of escalation on concrete and steel and wood and stuff is more than the premium that we paid at that time for having all the technology and the stuff that gave us benefits.
And that's a footnote we need to add in our. That's why it's still not released. But that's also important to remind people about. If you were a corporate campus in Atlanta, your cost premium would have been 12.7%. It would have been lower because you'd get the almost 50% discount for your solar system. And those numbers don't seem astronomical when it comes to upfront costs, considering it's like you're purchasing 30 years of electricity, you've got a rainwater drinking water system. Then we have to consider operational costs. The operational costs for one category, the foam flush toilets, is actually remarkably low. It's not even $9,000 a year. That's actually amazing considering you're composting poo and pee, you're not hitting the sewer system. I mean, $9,000, not bad. The compliance cost for rainwater or drinking water is $50 grand a year. And paradoxically, because we have a foam flush toilet system, we're not using a lot of grid water. So we're not saving a lot of water. And we just liken it to a pure R&D, first of its kind expense, but if you are not doing it for altruistic reasons, that one decision blows your monetary ROI. So what is the as-built monetary ROI for Georgia Tech? Anyone want to guess? It's a lot worse than I thought it was going to be. Anyone? Anyone? Going once? 45 years. Maybe. It actually extends beyond the graph. It just extends. I had guessed 25 years. It's 45 years. For a corporate client or hypothetical corporate owner, it's 33 years. So when we looked at the expenses, we said, well, what if this had a resilient water system, not a regenerative water system? And resilient is the grit, we have a boiled water advisory. The building still has enough water. Instead of a water treatment skid, we have a water purification skid. If anyone's been to the Interface headquarters in Atlanta, that's what they have. We added some costs, we reduced costs, and we took out the $50,000 a year. We have a 10-year improvement. All right? 10-year. Yeah, so it goes from about 45 to 35 for Georgia Tech, and it drops to about 22. And then what we did is we started looking at other things. The first thing is this thing. This is exterior automated blinds, $150,000. I understand why we did it. My recommendation is not to do it. Triple pane windows. I mean, the building is so efficient. The thermal advantage you get from this, I don't think is worth the operational headaches, or because it's already broken down once or twice. And so if we remove this, it's about another year benefit.
The blind. They're outside.
They're external. And so when we were designing the west facade, and I hinted at this before, right? The PV array comes way out as an overhang. It does a great job shading the second story. The first story, the cutoff angle is not nearly as good, right? And so that lower story needed some help. And what we did was, there's a row of trees that are planted there, and the idea was by the time the trees are old enough, so think 15 years from now, the life cycle of that shading system will have been shot. It will never need to be replaced, and the trees will become the shading device. And that was the way we approached the problem. In hindsight, we probably should have taken 150 grand and bought bigger trees.
Bought bigger trees. Yeah.
I mean, that's
yeah.
well, what can you do? You know, it's like.
Well, and then
I don't say it that bluntly in the report. I say something like, those funds might be better used for landscape improvements.
yeah, and then mention about breaking down. So maybe something happened, a student ran into the wire. So
Show us what happened.
yeah, and so it breaks. So that's fine. We order it. It turns out, of course, then we have all these supply issues. So the manufacturer's out of Australia. We didn't get the replacement. I mean, the one little run, it took a year. It took a whole year to get one run replacement on that thing.
So that's a lesson learned too. When you're thinking about what type of solution, is it mechanical, will it break? And if it's mechanical and it might break, let's think about something that's more passive, right? So that's a lesson learned.
I will also say, relative to this particular system, Georgia Tech was, Sean, before you came on board, was appropriately apprehensive about the system. And we put them in touch with other building owners who had similar systems, and they were reassured, particularly the system on the Bullitt Center. Well, we wrote a spec, had to be competitive, and the manufacturer that's on the Bullitt Center is not the manufacturer that won the bid. And so one of the lessons learned here, certain things are probably worth a proprietary specification, especially for a system like this that can be prone to significant maintenance / failures and headaches.
And the system works now, but honestly, we should consider just turning it off.
Yeah,
I mean,
it does work, but so yeah, here you see another lesson learned, and it's what you don't see, which is it's that this is triple pane, this is triple glazed windows, $350,000 premium. But it's interesting. If you take this out, you get like almost 3-year benefit in monetary ROI. And as the building owner representative, I have gone from, I wouldn't do that again. We over-engineered the building. We got to net positive energy. Triple pane, triple glazed windows have more carbon pollution baked into it. Not sure if we went through all of this. And then every single time I leave the building and hear the loudest building on campus, which is right next door, the Marcus Nanotech Center, which I was reminded on Thursday when the three of us had a conference call for this, and I was driving my way up here, walking in my car, and I couldn't hear them. Imagine how loud that building is. This building is pin drop silent. Over there, no knock to Georgia Tech, but our existing fleet of shuttles might as well be in India. And I can get away by saying that because I'm from India. I'm like, what the heck is going on with this stuff? I think it might be illegal in my hometown. It's loud. This building is exceedingly quiet, which gets us to the non-monetary aspect of what we've done. What is the monetization of the health? And here it's the quietness. That's outside the scope of our report. But what I say as the owner is this triple pane window might not have made sense from an energy perspective, from a cost perspective, from a carbon perspective, but we might have ended up doing it anyway from the health and happiness perspective, because it is an exceedingly quiet space. The students have decided that it is a library, not a place to hang out. When we are, our voices carry. When we're giving a tour during school session and I get overly animated, I know it might be hard for you to imagine me getting overly animated, students will look up and, sorry. I think it is a totality of what they have designed and what they have built. And so it comes together. So what we're saying there is that there are, in fact, non-monetary reasons to do something. And we purposefully have not gone down that road because the metrics behind some of that analysis is fuzzier, right? We are really focusing here on first cost, financing, ROI type stuff, right? That's really what we were trying to get at, is to lower the first cost. The kicker is we go through some other stuff, and we get to about a 17-year return on investment for a corporate owner. Radiant floor is in there, but we neither make the recommendation of keeping it or removing it for the reasons that Joshua said. We think that if you got rid of radiant flooring, you would have to have some type of solution, and it might be the same cost. It's just we didn't want to go through the nitpicking, but we put it out there as something that you might want to consider. The conclusion actually asks us, and this is ultimately the lesson learned. Even at a 17-year return on investment, most CFOs will tell you to get out of the room. And the reason why this thing has a 17-year return on investment is exemplified by this picture. And this is a picture of stuff being thrown away. What I tell folks on a tour is that when you are designing with artificial constraints of net negative waste during construction, 100% in our case, 90%, we achieved 100% stormwater diversion. Beginning your life as a carbon zero building, these are constraints that conventional buildings don't have. Our ridiculously bad return on investment is because pollution is subsidized. This is subsidized. This is not this picture of a dump truck dumping garbage in a landfill is the poster child of subsidy, because in a natural system there's no waste, right? In a human system there's waste, and it's only because we made it cheap to waste. Like, this is irrational market behavior, except it's not, because we all do it. It is cheaper to throw something away than it is to do what Joshua and Jimmy and the entire village of this building did, which was designed for not waste. That's the moral of the story. That's the lesson learned. All right.
Just the PV system wasn't too bad. I mean,
No, just the PV system.
it was pretty good.
It's pretty good. Just the PV system is pretty good because every electron that's exported out of the Candida building stays within Georgia Tech. So even though we pay about 6.1 cents a kilowatt hour, we are on what's called real-time pricing. So at times, Georgia Tech, especially this past summer, was paying $1 per kilowatt hour. That's the same time that the Candida building was probably 500, 600, 1,000%, 2,000% net positive energy. And that's when our excess electrons are providing the most benefit to Georgia Tech. They stay on our campus. The reason why the hypothetical for-profit company is a widely held C Corp that has built the Candida building on its corporate campus is because the excess electrons stay behind the meter. So it's a very specific use case. By oversizing the solar system for the corporate, hypothetical corporate, it is a 10-year, 11-year return on investment. No, that's with the tax breaks, because that's the corporate. But for Georgia Tech, it's 16, so even that is pretty good, right? Or 17, yeah.
Back on the triple glazing, who's the manufacturer?
Conair.
No, Conair is the system. I think it's Viracon.
Oh, the glass is
Yeah.
Viracon
Yeah.
itself. Yeah, Conair is the system.
Yes.
Yeah.
Yeah.
Okay, so, and did you do any tuning for solar heat gain coefficient on the east and west facades?
No. So what we did with the glass. So a couple things. So one, we made the decision from an energy optimization, an operational energy optimization standpoint to go with triple pane glass. I would say that our mechanical engineer was PAE. Mark, we heard from at lunch, a friend of mine, he was the lead engineer for this project with us. When PAE went to do their own living building, the one that they were talking about at lunch, they actually did the analysis and decided they would rather pay the energy penalty than the embodied carbon for a third piece of glass, and they went with double pane glass on their building. So the logic and the questions that we ask the answers are different on every project, right? It's about context. It's about what you're trying to do, where you're trying to go. But where I was going with that is once we made that decision to go with triple pane glass, what we end up with is a system that's not 1 inch, right? So we need a curtain wall that's got a little more depth so it can hold the system, and that has extra weight to it. It has all these other things that go with it. Somewhere along the line, we had call it an epiphany brought on by the Candida Fund, who said, well, have you guys looked at bird strikes? I said, well, probably not as much as we should have. And you'll see, if you understand bird strikes in buildings, one of the big problems are transparent corners amongst as well as reflectivity. We've done a really good job. We specified glass that was not reflective from the outside, but we definitely had some transparent corners that were a problem. And so we used frit on the glass to make the glass visible to birds. And if I had to do it over again, and if we were going to do double pane glass, then you can do a laminated IGU with a third piece of glass, and you can put the bird safe layer, which is an IR laminated product, in the IGU, and that's a much more effective way to prevent bird strikes.
Not for my sake.
What's IGU?
What is IGU? I'm just going to call it out.
Sorry,
For those of you who don't know what I know, it's for me.
Insulated glass unit.
Thank you.
It's the sorry. But we ended up with, we couldn't do the inner laminate because we already had 3 pieces of glass in the insulating side, and so that's why we ended up with a frit on the number 2 surface, and so that's our bird strike prevention. And through collaboration with yet another community partner, we worked with Georgia Audubon, who is now using the building as a case study, and in fact is now studying buildings throughout Georgia Tech's campus to look at the effectiveness of that as a bird strike deterrent.
And I have seen a bird flying right to the building, and I have seen that bird get really close and then go. So that bird survived. The health and happiness of that bird survived.
So the frit actually
The little dots.
the frit it's a 1/8 inch dot at, I don't remember the spacing we specified, but nominally it probably about 3/4 inch centers, and so it's a grid pattern throughout the glass. It is not visible unless you are extremely close to it.
Yes, I can attest to that.
It is a bit bird ethics because it prevents like 97% of strikes or 94% of strikes, and so which one do you pick? The 97, the 94?
One last question on glass. So, some percentages around double glaze versus triple glaze in your energy model. Or do you remember what the
What the difference was?
What the energy penalty was?
It'll be
Yep.
in the final report because I have to email Mark to next week to ask for it.
I would say off the top of my head, I do not remember that detail.
But it will hopefully be in the final report.
Related to that, how much impact does the triple glazing and the radiant floor have on this perceived comfort? Because you talk about perceived comfort from radiant heat, but then saying you might value engineer those 2 things out might really affect that. You would have to put
especially with high ceilings.
Yeah. So I think the answer is tremendously. Right. I think radiant. So for the record, radiant heat is absolutely imperative to the functioning and the comfort of the building. Radiant cooling is what I was questioning. But
a lot of studies have come out recently. LB Hills is doing a lot of work on this, showing that our perceived comfort is a lot based on
no, it is. So yeah. Yeah.
you don't have to run spaces as cold.
Yeah. So the diagram that we had up here before, the wheel with the six factors. So that wheel, the issue is that mean radiant temperature is super important, right? And and that has a huge impact on your perceived comfort. And that's no, I think what I should be more nuanced in the way I said that. So last summer, not this summer, but the summer before that, the building ran using nothing but dehumidification as the driver, and the building met the set points, and the cooling slab never came on.
Nor this summer.
Nor okay, I wasn't sure about the summer too.
Yeah.
So
That's
what
we
we're
mean.
that's what I'm talking about. It is not completely necessary to make people comfortable because we're meeting the thresholds without it.
And I wouldn't necessarily take the concrete slabs away, though, right?
Right.
Yeah, you
Yeah.
need the thermal mass. Absolutely. Yeah.
Because you've got, you're saying you run at a 78-degree set point. There's something happening there with the radiant comfort that's enabling.
Right.
Well, don't forget, we also have ceiling fans. We have ceiling fans throughout the space because we're trying to harness the idea that air movement helps you feel comfortable.
I just don't know anything about glass, so is the triple versus double affecting the radiant energy at all?
Yes, it is. Yes, absolutely. Yeah.
It does because if the inside surface of that double glazed unit is going to be more like closer to outside than a triple glazed unit.
Right.
That your body also
Everything
has
and everything else.
Right.
effect on your skin.
But let's
Correct.
talk about
That's-
how we accidentally found out that the dedicated outdoor air system can provide a lot of cooling in the summertime. Anyone?
Is that, by the way, is that those big ducts on the ceiling that we kept on the roof?
Yeah.
That's how we move that air.
Yeah.
It must have a hell of a lot of insulation.
It does. Yeah.
So COVID hit, and we decided that we are. COVID hit, and we decided we're going to have to. The building did not shut down. We still had occupancy. We were just at reduced occupancy. So we decided we were going to, first of all, open up just open it up. I mean, we opened it up. So for March, April, it was like we were in a. It starts with a P.
Pandemic.
No, the other. And it's not a. Okay. But you know when it's not a building, it's not a
Pavilion.
pavilion. And I was thinking pergola, and then I thought pagoda, but I knew it was pavilion. So it was like a pavilion, and then it got humid, and what we did is, does anyone watch Spinal Tap? We turned the dedicated outdoor system to 11. And we were just bringing in so much outside air that my country lawyer was like, them doors broken. And they're like, no, there's so much inside air going outside that the doors just wouldn't close. And then I said, why is there condensate falling in certain areas in the building? And the answer was the dedicated outdoor air system is pulling in so much outside air. We have chilled water coils to help with the dehumidification, and the air was coming in bonkers cold just from the dedicated outdoor air system, which got me thinking. I said, hey guys, come to the building because I'm wondering, did we need to do radiant cooling? Because the engineers are telling me it's not coming on. This building is actively cold in some spaces. Could we have just designed the building to cool with the dedicated outdoor air system and had like a drip tray to catch the condensation? But that started, I mean, no, look. But that started the conversation of whether, this is last summer, summer of 2020, if we could think that far, the first summer of COVID, started the conversation and the thought process as to whether the radiant heating system was needed. Then winter hit, and what we found was that in the winter time, the two zones that come on this past winter when the building was fully occupied and humans could heat space just through their body heat, two zones of the building's radiant heating system turn on the most. It's the zones immediately inside the entrance doors. Other zones of the building aren't turning on. And the building is comfortable. in the wintertime with most of, and we moved the set point to 70, by the way, in the winter. It used to be 68. We've sent it to 70. So yeah, but you know, all buildings are unique, right? I mean, unless you're a mass, you know, multifamily, this is just designed to. This is an exercise of, okay, what would we tweak to get the first cost down?
What is your outdoor air ventilation rate? Is it hash rate now standard, or are you working at double, triple that?
It's more than
Well, the design was 15-20%. No, just to move the air. But during COVID, they like doubled that. They did a lot of circulation during COVID, and I think they've kept a lot of that. So they've been moving a lot of air.
Yeah, we actually Georgia Tech tried to get the building to 100% outside air during COVID, which the system isn't designed to do that. Right, the air handler's not big enough. The CFM didn't exist, but they got to about 50%, if I remember the conversation with Greg, who's the campus engineer, correctly. So.
Have y'all looked at standards like reset and just evaluated where you landed on their framework for air quality?
Oh, the air quality.
Since the building has been built, no, but the Living Building Challenge requires comprehensive air quality testing as a part of the certification process. And so and one of the things that we were worried about, we were certifying in the summer, or we were doing the air quality testing in the summer, and Atlanta's primary air pollution problem in the summer is ground level ozone. And so we made sure that the air quality testing requirement, which is also part of the LBC, is we had an outdoor baseline because we needed to compare it. So if our ozone levels inside were elevated, we needed to know if it was because they were elevated outside or not. But we comprehensively tested the building. We failed one of the tests because someone, keep in mind this is like, someone left a packet of Clorox wipes out.
Oh yeah,
on a
one
conference
conference
table.
room we failed a test because
So if you ever started wondering if those things were good for you, the answer is no.
of the COVID wipes. Yeah.
I have something to add about indoor air.
So we passed the actual tests with flying colors other than the Clorox wipes. And it's amazing. And then also there's been students, Sean, you might know more about this. They've actually been studying the building continuously through time. There's sensors in the building that live do it, and they judge other buildings, and I'm pretty sure it's the best performing on campus.
Except, and this is a little funky thing. They were reading more indoor ozone in the Candida building than they were reading in other buildings. And they came to me and said, why do you think it is that we're reading higher levels of indoor ozone than other buildings? And I was like, it's probably because we're bringing in more outside air. And so we are very close to the downtown connector, which is a euphemism because it splits the city in half. It disconnects the city. But it's 75, 85. And if you've ever driven through Midtown Atlanta, it's a parking lot for many hours of the day. And all of that ozone in the summertime mixed with the naturally occurring ozone that is coming from the eco commons, 8 acres that we've rewilded, that ozone is coming into the building. And it's, is it a health issue? I don't think so, but it is an interesting outcome of bringing in outside air because the connector is adding onto what would be naturally occurring ozone in that area.
While you're talking about systems, what are the lessons you've learned about, I guess, designing for the long term and how you thought about those systems and how are they going to be
Long life and spit.
replaced, repaired, upgraded? So something like your radiant floor or radiant cooling, you know, that's a difficult replacement or repair if that needs to be done. How did those design considerations come on? It's you know, when new technology comes up, can things be upgraded, changed?
One thing I'll mention is at the beginning we were doing geothermal wells. We actually took it through the end of design development. We were 35, 500-foot deep wells, or tie into the campus chill water system, and ended up costing about $600 less to tie the chill water system, and it was kind of actually nice to have that district energy from the campus. Also in the wintertime, our chillers actually give that system energy. When we heat our floors, we actually give chill water to the campus. So that's an amazing little system thing. And so because we're tied into that central plant, that is an example where if one day that central plant modernizes, it can happen in that one place, then benefit all of campus.
And I would say architecturally, we actually spent quite a bit of time thinking about the issue that you're raising, right? And we started throwing around the term long life, loose fit for the building. And so what we've got is we kind of divided the building into a hierarchy of walls, right? Walls that would be permanent, put that term in quotes, right? Nothing's permanent, but permanent-ish, more permanent than others. And then walls that were more demising walls that would be designed to easily come down in the event of a renovation. And so anything that was noted as a demising wall would have nothing in it but power, right? None of the manifold piping for the radiant, no HVAC, nothing, just studs, sheetrock, and where we needed it, power. And the other thing we did relative to that, then the teaching laboratories, which are the eastern block of the building, are laid out. We talked earlier in the previous session about our structural grid, which is 10'6". If anyone's familiar with laboratory design, 10'6" is a really common lab design module. And so what it allows us to do is pull out the walls that are parallel to that structure over time and create a long open lab across the eastern flank of the building on 2 floors if we wanted to. And so we were thinking about it in those terms as well.
And then the auditorium is flat and not theaters. What is it called?
It's not tiered.
Tiered. To the chagrin and disappointment of one extremely opinionated economist who is an expert architect. I'll tell you that story in a moment. But it's because in the future, maybe we want that to be a ballroom. We don't know. We got 3 minutes left, and I want to just highlight this chart that Joshua Gassman reminded me about like 4, 5, 6 weeks ago, and since then it's become like a thing that I do all the time. Percent of total life cycle energy carbon. This is a lesson learned on how important it is to begin a building with exceedingly low embodied energy carbon, whatever you want. Joshua, why don't you explain this? This is yours. Oh, I don't want to take it from you.
You're welcome to take anything you want. This is all good.
But this is scary.
So
like the explanation of this is scary. It really is. Okay.
All right. So this is in graphic form what I was saying earlier about embodied carbon, right? So if you take any building and you assume it takes X amount, in this case, not only 20% of the life cycle, but it doesn't matter. It's a baseline, and that baseline you have embodied carbon to build the building, and then you open it, and then for the rest of the life of that building, it has embodied energy that accumulates over decades, assuming the building is up and running for decades, right?
Operational energy.
Yeah. And so click one more time. Okay. And so if you have a really high performing building, let's call it a LEED platinum building, and I don't say this to disparage USGBC or LEED, but just these are not net positive or net zero buildings, right?
They're
So it
sustainable
has-
buildings.
Yeah. That term in quotations. So it is, in fact, a building that continues to build on its carbon footprint through its lifetime, through its operational energy that is on top of the embodied carbon it took to build the building in the first place, right? So you go to a net zero building. Now your operations are zero over a course of a given year, but you still have your embodied energy that you put in the atmosphere to build your building at the beginning of its life, period. You need to go to net positive to start to pay down the embodied carbon that you used to actually build the building in the first place. And so this is the realm that living buildings are operating in, right? We're talking about net positive buildings. Now the steepness of that curve, whether it's 50 years, 20 years, less, 5 years, someone do a zero for me. Come on, we can do it. Then this is the lesson of let's call it reverse compound interest, right? It's the opposite of why you want to invest early in a 401k so it builds over your lifespan. This is you want to not put carbon in earlier now because any carbon we put in the atmosphere now means we have to take that much more out in the future.
And this is drawdown. If you're familiar with drawing, the whole concept of drawdown, the Candida building began its life not here, but here. And I'm not counting the offset that we had to pay. We got our embodied carbon as low as we could. And so from an operational perspective, one day we might do the analysis, we are drawing down atmospheric carbon much quicker than had we even started up here with net positive energy.
So as an industry on the embodied carbon side, not the operational side, we've done a lot of work in the last couple of years to add as a selection criteria embodied carbon. So, it's not just the strength of the performance of these products and the cost, it's also like how much carbon. So if you got a 3,000 PSI concrete mix, there's a way to do it where you use a little more CO2, and maybe a way to do it use a little less. And so the smarter we are at adding that as a selection criteria, that will then enable the industry to then have strategies to lower their carbon to become more competitive. So let me just give you an example. At Skanska in Sweden, we have a huge market share. So we own our own mines and quarries. And so one year we did an experiment where an entire mine quarry was, we had a partnership with Volvo, and they did all battery operated mining equipment. And then that battery was, the equipment was charged from wind turbines. So the whole thing used no fossil fuels, and it operated an entire year using no CO2 emissions. So if you did something like that, you could see how the aggregate from your concrete could come from a zero carbon source, and then we could be incentivized because you'd be more likely to select that kind of product because they did that kind of thing, right?
Good. Just a couple of quick additions in terms of Chattanooga, right? So like in Southeast Tennessee, there is no fossil fuel emission from electric generation. We've got nuclear, we've got hydro, right? So from a technical sort of TVA carbon accounting standpoint, we still have to take credit for all of the fossil fuels in TVA's entire grid. But if you were to just literally draw a circle around Chattanooga, we are not emitting fossil fuels in our region for the electricity. We are emitting a ton of carbon over at Bootsy at the foot of Signal Mountain to create Portland cement for concrete. So just as an unbelievable amount of coal is burned at Bootsy to make concrete. So this is a really important concept to grasp for Chattanooga, because arguably that's more important than even the operating energy from a carbon standpoint here.
I would actually argue that it's more important than operational energy, period.
Yeah. No, I agree.
Yeah.
I agree.
And in part because over time, fingers crossed that legislation doesn't continue to undo this, right?
Yes.
Over time, the grid will clean itself, and eventually we will get to a point where we have a carbon-free electrical grid, hopefully before it's too late.
Fingers crossed.
And then we can...
Right. Also right.
No,
so
so that's all. It's also predicated on the fact, on the assumption that these are 100% electric.